all we have left is this circular arc right over here, which we can find the area of, since it's just 180 minus 2 theta divided by 360, all multiplied by, well, L, it should be pi r squared, so pi L squared. So we get this is 90 minus theta over 180 times pi L squared. And of course, we know the value of theta is cos minus 1 of A over 2L. So we divide that by 180 and we multiply it by pi L squared. And of course, this is summed to exactly half A squared. Now that's a very tricky task. Essentially, most of what we usually do here is just, it's just plug in. Because plugging in here, I don't exactly think I can solve for a general solution, although I'll definitely try. So we get, how would I find an explicit solution? Squared is equal to, let's multiply both sides by 2. A squared is equal to 90 minus cosine minus 1 over 2L over 90 times pi L squared plus the square root of L squared minus A squared over 4 times A. Yeah, this doesn't seem very possible to do without plugging in some value for A. Like for instance, if you plug in 1, suddenly this becomes a lot easier to find a regular explicit form for. So let's see, can we find an explicit form for L if we plug in 1? So this is still, of course, a lot harder than you would expect, but I think it should be possible, theoretically possible. So I'm going to start by multiplying both sides by 90 over pi L squared, and this is equal to 90 minus cosine inverse of 1 over 2L plus 90 over pi L squared of the square root of L squared minus 1/4. So then all we really do here is we are going to factor out 90 from here to get 1 over pi L squared minus 1 over pi L squared rad L squared minus 1 over 4 minus 1 is equal to negative cosine minus 1 over 2L. So that means that we just have cosine of 90 times this is equal to 1 over 2L. Okay, this is actually a little bit different about this. So this works, but it's not an explicit solution. So let's see, how easy really is it to actually find an explicit solution? So here's the strategy I'm going to use. There seems to be no better strategy than just letting it be a circular arc, but I'm probably wrong. So let's draw the full circle, and then, so let's see. Okay, so we're drawing the full circle, and we have the square right over here. So it has area L, this has length L, this has sine length A, and so let's see. So L definitely has to be bigger than A over 2, of course, so it can't be a diagonal like this. It has to be something like this. So you guys, okay, so something like that, which, let's see, what can this end up being? Is there any way to actually calculate it from the opposite side, for example? So let's see. We have, okay, I'm going to try and calculate these in a bit of a different way. How would I know about this? Okay, let's see. So, of course, it doesn't matter what A is, because then you just multiply L plus the proportionality constant, So what I'm going to do is set A to 1, which makes this 0.5 and this 0.5, and then solve for L, which can't be that hard. So let's see, this is going to be, and actually instead of this, let's make it 2. So half of it gives us 1. So we have 1 right over here, and of course, this is just going to be tan theta. Yeah. So this is going to be tan theta. This is also going to be tan theta. Let's see if we can make it in terms of these functions. So we got tan theta is the area of the rectangle. And then what's the area of this? Well, it's just going to be pi L squared once again times 180 minus 2 theta divided by, okay, so then we just have to find theta in terms of L, which gives us something kind of nasty because then theta has to be, theta's going to have to be, yeah, same thing. So just be cosine inverse of 1 over L. That's not what we exactly want to have. So, let's see, cosine inverse, tan of cosine inverse of 1 over L. I think it's best to write it as square root of L squared plus 1. Okay, so we have the square root of L squared plus 1. And then so we still just multiply this by 180 minus 2 times this theta, cosine inverse of 1 over L, and divide that by, okay. What I'm going to find here is instead do this, because this is actually going to be the square root of L squared plus 1, so that we can write this as something separate. Instead, we might be able to write it as tan inverse of L divided by L squared, the square root of L squared plus 1. And finally, this has to all be divided by, so I'll write this as 2 tan L over tan inverse of L over square root of L squared plus 1. And then we divide that all by okay. So I'm not going to solve this one right now because I feel a little bit stumped, but let's see. If there's any way to, no, there's no quick and clever way I can see to solve it right now, but it's definitely a very interesting problem. Let's see if there's one more little thing I can do. So let's see. We want this to be exactly half, which means it has to be rotative. Okay, so here's what I'm going to do then. I'm going to take this whole thing, will just be all we need. This is L squared plus, the square root of L squared plus 1 times 2. Let's say that. And then all we need to do is calculate this to finish it off. So what is that going to be? Well, that's just going to be, I don't want to make this any smaller than it is. Okay, I don't want to spend too much time on this one question, but it's very interesting. I've seen this riddle before, but unfortunately I don't need to remember the solution right now. But I think all you have to do is follow this general strategy, although I'm unaware there's probably some other strategy that you might be able to use to get it. Something where maybe where we draw tangent lines like this. But right now, I'm kind of not coming up with any ideas. But thank you for the question. Very nice. Fine x over x, okay. Oh, yeah. Okay, so the integral of sine x over x should be fairly simple, I think. So all you have to do is do double integration by parts. So you just choose the integral of sine x over x. This is sine x times 1 over x dx. So you do this dv, this du. So we get that the integral of this should be 1 over x times minus cosine x, since we're integrating it. And then minus cosine x times the derivative of this is, of course, minus 1 over x squared. So these cancel out, dx. And then all we have to do is just take, oh no, it's not happening. Oh yeah, should be. So all we have to do is take this to be dv and this to be du. So then this itself is going to be equal to cosine x times the integral of x to the minus 2 is of course minus x to the minus 1. So minus 1 over x. And then we add that to, we subtract that from the integral of minus 1 over x, and of course the derivative of cosine x is minus sine x. Oh. No, this is a circle. This gives us a circle because these two are the same exact. So let's doing the same kind of strategy, we only widen the circle. So we have to figure out some other way to do this. I think I can come up with an idea. So let's think. 1 second. So is there anything I can do here? Well, okay. Wait a second. So wait, isn't this pi? Okay. So it is pi, but of course I can't just do that without verification. So no, it's integral. Yeah. Oh no. The graph looks like this. Yeah. So integral should converge. In fact, I believe it's actually pi. But I forget how to solve it, so let's see if I can do anything to solve this. So, how would I actually compute something like this? There's probably some clever trick which I'm not seeing. So, can I substitute anything in? Can I go to polar coordinates? Is there any other way for me to do this that I'm not already seeing? So, no, going in polar coordinates is only going to result in something else. Wait a second. Oh, yeah. Wait, I think I have an idea. The Taylor expansion of this is equal to x minus x cubed over 3 plus x to the factorial, 5 factorial minus 7 factorial, and so on and so forth. So what I'm going to do is, I'm just going to divide this by x. This is 1 minus x squared over 2 factorial plus x to the 4, x2 over 3 factorial plus x to the 4 over 5 factorial minus x to the 7 over 7 factorial, x to the 6 over 7 factorial, so on and so forth. Then we're just going to be taking the integral of that. And what's that going to be? Well, it's going to be x, x minus x cubed over 3 factorial times 3 plus x to the 5 over 5 factorial times 5 minus x to the 7 over 7 factorial times 7 and so on and so forth. So of course this doesn't give us anything quite yet, but I'm sure we can find some Taylor series which uses this. So Taylor series does Sn x times x to n divided by divided by n factorial. So that means that x to the n is already counted for. So that means that f of x always has to be equal to, okay. So let me think about this for a second. It should always just have to be equal to, the n, right? Yeah. So this should just have to be equal to, we're taking the endless derivative of this. Right, okay. So, we're taking the derivative and, oh, okay. Right, I'm going crazy today. This is equal to 0. So that means this at 0 has to be equal to 1 over n factorial times n. This has to be equal to 1 over n. Okay? So that means that what? Well, if f of 0 is 1, f prime of 0 is f. If f of 0 is okay. Oh, okay. So f prime of 0 is 1, f of 0 is 0, f double prime of 0 is again 0, f triple prime of 0 is a half, so on and so forth. I mean, this doesn't make that much sense in my opinion. So, how does this from minus infinity to infinity approach pi? Thinking for one more second, because I think it might be wiser to just take this part and use the box. Let's see. Wait, let me take the derivative of this. Let's say this is f of x. What's f prime of x? This is going to be 1 minus x squared over 3 factorial plus x to the, oh, I just did that. Okay. Okay. Anything else? Okay. So, I don't think I can solve this right now. Let's see, is there anything else I want to say? Do I have to simply sum over and sum? Because, I mean, that doesn't seem like the right way to do things. Sum from minus pi over 2 to pi over, what, that's no science. Sum from pi over pi to 0, from 0 to minus pi, and so on and so forth. Because that doesn't seem like the right way to go about things. Wait. Okay, I think it might be solvable by this method. So we take 0 to pi of this, which is of course going to be pi minus pi cubed plus, and what I'm going to do is I'm just going to take the positive half of this to save me some time. 0 to pi over 2. If going over that, that's going to be pi over 2 minus pi over 2 cubed, 3 factorial times 3, and so on and so forth. But then we get to pi over 2 to 3 pi over 2. So then we subtract this whole thing, we add 3 pi over 2. But then we subtract and add again, and we keep subtracting and adding. It seems to me like it would be a telescoping series. So it should approach whatever this approaches as x approaches infinity. So that's not, it's not very descriptive, of course. Because that's literally exactly what we're going to state. But let's see. No, I don't think there's anything else useful that I can provide. So yeah, I don't think I can solve this now. Some of it will find x over x.
Yeah. So here's your questions now. Are you ready with the question?
Greetings, I'm Sabri Asmin. I'm from MIS Gopalnagar and we have met before RPN. The question I want to ask actually I need to story. There is a staircase and it has 2 steps on it. What's it?
Okay, that's a very good question, but actually, it doesn't have to look like that. So the picture you drew was like this for the first iteration, then like this for the second iteration, or technically the fourth. And then you assume that for infinity, it should have looked a lot, right? But the thing is, there's no reason it has to look like this. In the same way, it could look like this, and then all the other infinite steps are just squeezed in a bunch at the bottom. So actually, the total length of this is going to vary. It's not always going to be long. But then, what about the point, at the point where it is, right? So, you already know this is A1, A2, A3, A4. And the best practice to do in this situation is, I think, not to take the sums of these themselves, but rather the sums of their hypotenuse. I think that will give a better illustration. Let's see. So, A1, A2, A3, A4. Oh, wait a second. Okay. I think this is the exact same argument. The reason why pi is equal to 4, because you can draw a square over here, then you can draw a square over here with, you can draw a shape over here with less area between it, but the same length. Same thing can happen over here. Then you can just keep optimizing it until it technically looks like a circle. But it's at some point it's still a square. Okay, here's a better way to explain it then. So, the thing is, if you zoom in enough, eventually there are still going to be these little discrepancies. And as they approach infinity, sure, they're going to get infinitely small. We can call them dx, and maybe dy as well. But then once we integrate over them, since there are infinitely many of these infinitely small steps, they're going to become a finite amount. Kind of like how, if you have something that's curved, if you have a line that's curved, initially you're taking these rectangles under it, but once you take the integral, it's like summing all of these rectangles, which are a very small distance, kind of maybe also a relatively small function. But once we sum over them as part of the integral, it's no longer that small. So essentially what I'm saying is, these may be infinitely small steps, but there are also infinitely many of them. Kind of cancels it out of them. I know, it's not very clear to say, but let's see. What's a better way to explain it? There's no point at which you can simply remove this discrepancy. It visually gets smaller and smaller, the area between them, but that does not make the length any smaller than it originally was. So, even if the area gets smaller, the length discrepancy is always going to be the same. So just because the difference in area is equal to 0 does not mean that the difference in length is equal to 0. Is that a good way of putting it, or do I need to explain it a little bit?
Would you please explain it a little more?
Okay. So essentially, well, what I'm trying to say is that so no matter how far you're zooming in, no matter how far you zoom in, there's always going to be some point at which you can see the discrepancies again. So one way or the other, even though the area difference is small, as we said, at some point the area between this one, the staircase, and the line between it, at some point it's going to be 0, they're going to be indistinguishable. That does not mean that the length is 0. So for the sake of time, what I'm going to do is I'm going to assume there were n steps. And you can do, this was 3 and this was 4, so actually I drawn it the wrong way this whole time. So we look at something like this. Oh, no. Okay, so we're going to assume there are n steps. So an, since it's going to be the length, an is going to be 3 divided by n. And bn is going to be the height, so it's going to be 4 divided by n. So then, here's the thing. Of course, when you add 3 over n plus 4 over n, this is always going to be 7 over n. So then, when you add all the a_n's and bn's in total, 7 over n is multiplied by n is equal to 7. And of course, the limit, as n approaches infinity of 7, just this doesn't depend on n at all. No matter what n is, an plus bn is always going to be equal to 7 in the end. This is a 7. And of course, it seems paradoxical, but the fact that the difference in area is 0 between the two, or at least it approaches 0, does not mean the same thing as the difference in length is 0. And actually, this same argument has been used to argue that pi is 4. So, for example, you have a quarter circle with radius 1 right over here, and at first you have a square, or quarter square you might say, that encircles it, but then you slowly get more accurate. So you get more accurate every single time. And eventually, as you can see, the area between them is approaching 0. But everyone knows the perimeter of this square is 2, and the circumference of this quarter circle is just pi. It's just pi over 2. So is 2 equal to pi over 2? Is pi equal to 4? Well, no, because even though the difference in area here is approaching 0, at the end of the day, if you zoom in far enough, no matter how many steps you give, even if the area approaches 0, the length is not going to approach 0. So actually what I'm going to do is I'm going to find the difference in area. So, of course, when you have n steps, each of the triangles, each of the discrepancies is going to look like this, where you have an and bn. And of course, we denoted this as 3 over n and 4 over n. Meaning the area of these is 12 over n squared. And multiplying these by n for the n triangles gives us 12 over n. So the change in area is 12 over n. Which means since the limit as n approaches infinity of 12 over n is obviously 0, the change in area is going to be 0. However, the length doesn't hold the same way because instead of this being an times bn times n, this is an plus bn times n. So this gives us 3 over n plus 4 over n times n equals 7. So I know it's not a logical reason, but this is a mathematical reason for why this can't be true. Is it understandable?
Yes, thank you for answering the question.
Of course.
Thank you all for your questions. Now I will have questions on. Yeah.
Or you come.
Yeah, we also go through here and on which and theory. Please.
Good evening, everyone. My name is Pam Shetty from class 9. We know that everything was created according to Big Bang theory by Big Bang. So my question is that what was before Big Bang theory? And if it was nothing, can we consider nothing as the creator of this universe? And how can something create from nothing?
Okay, so that's more of a philosophical question than physics. Our observational tools would not be able to see anything that occurred before the Big Bang, because it would be a type of matter if there was anything at all that can't be seen anywhere in our universe today, and thus could never be detected by our own equipment. So we will never be able to know if there was anything there before the Big Bang. And in the same way, we wouldn't be able to know how something was created for anything that was there before. And the truth is, we only assume there was a Big Bang because the universe is currently expanding right now. So that gives scientists a reason to believe that it's always been expanding, which allows us to trace its history back to some point ago where it initially birthed. But maybe it was never like that. Maybe initially it was some small cluster that started expanding a few billion years ago. Or maybe it was just created in its present state and started expanding, or maybe it was just created, some 1 billion years ago. Oh, no, not 1 billion, that's way too ago. Maybe it was created, who knows, 6 or 7 billion years ago, and made in its current state. Or we already have reason to believe that it's older than 13 billion years old, not only because of the Big Bang, but because of sources of light that we can trace back to be 13 billion years old, but due to redshift. But one more thing, it could have been here for infinitely long, who knows, and just started expanding 13.7 billion years ago. So really, the Big Bang theory is just the most feasible or plausible one that doesn't require any mental gymnastics. But then, questioning what was before the Big Bang itself brings back the mental gymnastics in some way, because there is no way to measure what was there before, and there's no way to figure out how something before that we can't measure and that we don't know the properties of made something after, which we definitely do know the properties of. So it's more of a philosophical question than what you believe in than actual physical science that we can observe and theorize about. Thank you.
Any questions? I would like to see the whiteboard. Please.
What equals to infinity minus infinity?
Okay. This is not good because infinity has absolutely no meaning by itself. Infinity only means something when used as part of the limit, or very rarely in other expressions. But people like to misuse it casually. So essentially, most of the time we have limit as x approaches number. Limit as x approaches 7 of a function. But we don't want to break notation. But what happens if a function has limiting behavior that continues as it keeps increasing and never stops. So then, we say the limit is x approaches infinity if a function has behavior that is predictable and never stops as you increase x. So this just means as x increases. And in the same way, if you put negative infinity, it means as x decreases by condensing. But this symbol means absolutely nothing outside the context of limits, which means you can't just subtract one from the other. So infinity itself can't really be treated as a number. Of course, you've got the cardinalities of infinite sets, but those two can't be subtracted from one another. You can only create identical relations between the two. You can't make a difference between them. So once again, infinity doesn't really have a meaning outside of consistent limits, which means you can't form equations like this. Thank you.
Thank you.
We are taking the last questions of this question answer session. So you go here and ask the questions. Bye.
Good evening, everybody. My question to you is, why are some functions not integrable? And how can one determine whether the given function is integrable or not?
Okay, that's a very good question. So let's take the function sine. So let's take the function cosine x over x as a little bit of an example. So sine x over x, his younger brother, is very well behaved. It is equal to 1 right at its peak over here, and it slowly decreases over time. And of course it has a defined interval. But then, what about cosine x over x? Well, the thing is, as it approaches 0, this approaches 1, As it approaches 0, this approaches 1, and this approaches, 0. Meaning, this is going to approach infinity. So essentially, at some point, we kind of have infinite area that is occurring right over here. So, something like this, perhaps. And this is just completely non-integrable. I mean, how do you find the infinite area that goes on over here? So sine x over x is integrable, but cosine x over x is completely non-integrable because they don't have to over here. And in the same vein, we also have sine of 1 over x, which goes absolutely crazy when it's near 0. So this is what we call the topologist curve, and essentially it looks like this. So it calms down when it's not near 0, but then it speeds up in frequency until eventually the frequency is absolutely huge. And then as you get away from the origin, it slows down. So this is what sine 1 over x looks like. And as you get infinity, as its derivative goes to infinity, right around here, this is pretty much impossible to integrate, as you can see. I mean, how do you even integrate this? Because all these little infinite humps, they themselves, you have to add them all together again. It's just an absolute mess. So these are two functions that I would say are completely non-integrable. So if anyone knows of anything else, I'd be happy to show that. But yeah. So that's, 1 over x is indeed integrable. Of course, not from negative infinity to infinity, but it is integrable on the positive because it turns out that this area over here is finite, kind of like the area of a square minus a quarter circle. Turns out that this area is of course finite, and the integral of it is ln over x. So, I mean, I don't remember the proof of it off the top of my head. Let me think if I can write it quickly. But let me see. Can I? No, I don't think I can. But I think I might be able to. Actually, yeah. So we already know ln of, so what we want to prove is that ln of x and the derivative of that is equal to 1 over x. So then d dx ln e of e to the x, this is obviously going to be equal to 1 because it's ln e to the x. Wait, no, this is going to be equal to 1 because it's the derivative of just x, right? So then that should give us this by the chain rule is just going to be equal to f prime of g of x times d prime of x. So we have whatever ln, the derivative of ln is, times what's inside, multiplied by what's inside. So that means f prime of e to the x has to be equal to 1 over e to the x. So by the same logic, f prime of x has to be equal to 1 over x. So I think it might be a safety proof, but I think it's universal. So that's how I would prove that the derivative of ln x is equal to 1 over x. And thus, by the same reason, the integral of 1 over x is equal to ln x. So since ln x is not defined on the negatives, though, not at 0 either, that doesn't mean we can integrate it from minus infinity to infinity. It just means that we can integrate it from 0. It doesn't mean we can integrate it from 0 to infinity. So thank you.
Thank you very much for participating in the question and answer sessions by the all the students, new students of the Super 40 team project. So we do have the leader under whose the leadership the Super 40 Super 40 is being conducted doing well. Dr. Kazim sir is here. So I will have a few vision. Yeah. So before we take the Mr. Bari's views, I would like to take Dr. Kazim's views on today's event that has been taken by the Professor Suborno. I have observed as a mathematician few observations on today's event.
Thank you so much. First of all, thank you, sir, and thank you, Suborno,